Hi, this is the final video of this week. So let us discuss about Schwarz lemma. This is a lemma which can be used to characterize whole biholomorphic uh, maps within the unit disk onto itself, and it can also be used to characterize one-to-one onto conformal mapping between two disks. So the statement is very simple. We start from an analytic function defined on the open unit disk, such that its image is within the closed unit disk, and which fixes the origin. Then the symbol statement, absolute value of fz will be less than or equal to absolute value of z, and absolute value of f dash 0 is less than or equal to 1. Now, in addition, if there are some other points other than 0 with the same absolute value as its image under f, then if the absolute value of f dash 0 coincides with 1, then the function is obtained by a scalar multiple where the scalar is of absolute value 1. The proof is very simple. Just simply apply maximum principle to the redefined function f1z in this way. You will obtain the proof of course, you apply maximum principle in a smaller disk, I mean r less than 1, and finally you let r tends to 1 and you obtain the result. That is very easy. Now, let us see some immediate consequence of this result. So first of all, you can replace the unit disk by any disk. So you start from a disk of radius r, and the image is in the disk of radius m, and again which fixes the origin. Okay. So in this case, you will get some additional quantities will be there. You can notice that once m and r are equal to 1, then you end up with the classical Schwarz inequality. Now, in addition, if you have something like this, then it is obtained as a scalar multiple, the function, but this time c does not have the absolute value 1, but its absolute value will be something like this. This can be proved simply by considering a redefined function f tilde, where f tilde z is defined by f of rz by m. Now apply Schwarz lemma to f tilde, and you will end up with the result. Now the second consequence is that you can remove the assertion that it fixes the origin. Instead, it sends some z naught to w naught. Okay, so then also you will end up with the conclusion which is slightly different from what we had. So absolute value of m into fz minus fz naught by m square minus w naught bar fz is bounded by r into mod z minus z naught divided by r square minus z naught bar z. Now you can see that once you choose m and r equal to 1, you will end up with a very interesting inequality which is given as in the problem set. That is also very important. That is what we use. So that is something which you can use to obtain the so-called Schwarz-Pick theorem and characterize all analytic automorphism between the unit disk onto itself. So the proof is again very simple. The only thing is that in between we assert some we fit some linear transformation LFT between the disk of radius r to disk of radius 1 t, and the other linear transformation S from the disk of radius m to the unit disk. So then it's only a composition and apply Schwarz lemma. So that's all. Now, then here also you obtain this result. If equality holds for some z naught equal to z naught, and under these conditions, what happens is that this f is obtained as a linear fractional transformation. So you can combine all these results to obtain the result. Obtain that every one-to-one conformal mapping of a disk onto another disk, remember it is 1, 1 and 1, 2, it is given by an LFT. So hence it characterizes all the conformal mapping between two disks. So that's all from this week. So we will come up with new topics in the next week.